The morning mist hung over Aberdeen Proving Ground in Maryland as Captain Robert Mills and his team of engineers approached the hulking silhouette that had just arrived on a special railcar from France. It was late summer 1944, and this captured Panther tank represented everything the Wehrmacht believed made German engineering superior. Mills had examined dozens of tanks in his career, from early war Panzer IIIs to the latest Sherman variants rolling off Detroit assembly lines. But as he circled this 45-ton beast, running his hand along the interlocking wheel suspension system, he couldn't shake an unsettling feeling. Something about this machine didn't match what they'd been told about German efficiency. The intelligence briefings had been clear. German tanks were masterpieces of engineering, products of a nation that had perfected the art of mechanical precision. The propaganda Joseph Goebbels pumped out daily spoke of wonder weapons, of tanks so advanced they made Allied armor look like tin cans. German tank crews went to battle believing their machines represented the pinnacle of technological achievement, convinced that their sophisticated engineering would overcome American mass production. They had been taught that while Americans might build more tanks, Germans built better tanks. Every weld, every gear, every precisely machined component supposedly reflected centuries of German craftsmanship tradition. But here at Aberdeen, far from the propaganda ministry's reach, American engineers were about to discover something that would have sent shockwaves through the Wehrmacht high command. The Panther tank, the pride of German armoured forces, the vehicle Hitler himself had personally insisted be rushed to the Eastern Front, was about to reveal secrets that contradicted everything both sides believed about German engineering superiority. Lieutenant Thomas Crawford was the first to crawl inside the turret that morning. As an automotive engineer from Detroit who'd spent 3 years designing tank transmissions before joining the army, he knew what to look for. The smell hit him first, a mixture of hydraulic fluid, grease, and something else, something acrid that spoke of overheated metal and burned oil. His flashlight beam swept across the turret interior, illuminating the gun breech, the gunner's position, the loader's station. Everything looked impressive at first glance. The 7.5-centimeter Quak II gun was indeed formidable, capable of punching through any Allied tank at combat ranges. But as Crawford began examining the mechanical linkages, the traverse mechanism, the elevation gears, his trained eye began picking up details that made him pause. "Mills?" he called out, his voice echoing strangely in the confined space. "You need to see this." What Crawford had discovered would become the first entry in what would eventually grow into a 300-page report that would fundamentally change how the Americans understood German tank design. The turret traverse mechanism, which should have been a model of efficiency, was unnecessarily complex. Where a Sherman used a simple hydraulic system that any mechanic could service, the Panther employed a variable speed hydraulic motor driven by a secondary shaft from the main engine. It was sophisticated, yes, but it was also a maintenance nightmare waiting to happen. Outside the tank, Sergeant James Patterson, a maintenance specialist from the 2nd Armoured Division who'd kept Shermans running across North Africa and Sicily, was examining the road wheels with growing bewilderment. The Panther used an interleaved wheel suspension system called Schachtelaufwerk, a design that looked impressive with its overlapping wheels providing excellent weight distribution and a smooth ride. But Patterson, who'd spent countless hours in the field replacing damaged suspension components under fire, immediately saw the fatal flaw. To replace a damaged inner wheel, maintenance crews would have to remove multiple outer wheels first. What would take 30 minutes on a Sherman would take hours on a Panther, and that was assuming ideal conditions. "This is insane," Patterson muttered, shaking his head. "Who designs a tank that needs a full maintenance crew and half a day just to fix a busted wheel?" The question would prove more prophetic than he knew. As the team continued their examination over the following days, they discovered that the Germans hadn't just over-engineered 1 or 2 components, they had over-engineered virtually everything. The transmission alone told a story that would have horrified German crews who believed they were operating the finest machinery in the world. Where American tanks used robust, simple gear sets that could handle abuse and field repairs, the Panther employed a 7-speed AK, 7-200 synchromesh gearbox that required precise tolerances and careful handling. Master Sergeant David Klein, who'd worked at the Chrysler tank arsenal before the war, spent 3 days just documenting the transmission's complexity. "Look at this," Klein said, pointing to the gear teeth under bright work lights they'd set up. "These tolerances are tighter than what we use on aircraft engines. They're trying to achieve precision levels that make sense in a Swiss watch factory, not in a tank that's going to be crawling through mud and taking shell hits." The precision wasn't just unnecessary, it was counterproductive. The tighter the tolerances, the more susceptible the components were to dirt, debris, and the simple thermal expansion that came from regular operation. A transmission that might work perfectly in a clean factory would begin binding and failing after just a few hundred kilometers of combat operations. The third gear was particularly vulnerable, often stripping prematurely under the stress of combat maneuvering. But it was the final drive that truly stunned the American engineers. This was the component that transferred power from the transmission to the tracks, and it was the Panther's Achilles heel. The Germans had originally designed it for a 30-ton tank, but as Hitler kept demanding more armour, the Panther's weight had ballooned to 45 tons. Rather than redesign the final drive to handle the increased load, they had simply tried to make do with what they had. Captain Mills spent hours examining the final drive gears, measuring, calculating, comparing them to American designs. The conclusion was inescapable. "They're using straight spur gears where they should be using planetary gears," he told his team during an evening briefing. Germany suffered from a shortage of gear-cutting machine tools for the internal teeth needed for planetary gears, so they went with spur gears that are simpler to manufacture, but they can't handle the torque loads this tank generates. These things must be failing catastrophically in the field. He was more right than he knew. Unknown to the Americans at that time, German tank crews on both fronts were abandoning Panthers at an alarming rate due to final drive failures. French post-war reports would later reveal that the average final drive lasted only 150 kilometers before catastrophic failure, a statistic that would have been unthinkable in American tank design. Even German wartime reports acknowledged serious problems, with General Guderian reporting in June 1944 that the Panthers' final drives were failing well before the engines, which themselves only lasted 1,400 to 1,500 kilometers under ideal conditions. The engine compartment revealed another layer of over-engineering that bordered on the absurd. The Maybach HL 230P30 engine was a magnificent piece of engineering in isolation, a 700-horsepower V12 that could, theoretically, propel the Panther to speeds of 55 kilometers per hour. But the engine compartment had been sealed for deep wading operations, which meant cooling was severely compromised. The engine ran hot, consistently overheating, which led to blown head gaskets, warped heads, and catastrophic failures. Technician 4th grade Michael Roberts, who'd worked on aircraft engines at Wright Field, discovered something even more troubling. The fuel pumps were a disaster waiting to happen. Made with substandard gaskets that couldn't handle the heat and vibration, they leaked constantly. The leaked fuel would pool in the hull bottom, creating a fire hazard that had already claimed dozens of Panthers on the Eastern Front. At Kursk alone, 20 fuel pump failures had been documented in Panzerabteilung 54 by July 8th, with 3 Panthers completely destroyed by fires. "One incendiary round," Roberts said, demonstrating with his hands, "or even just an overheated exhaust manifold, and this whole thing becomes a crematorium." As the days turned into weeks, the American team compiled a list of over-engineering failures that seemed almost impossible to believe. The armor plate, while thick, showed inconsistent quality. Spectroscopic analysis revealed that the Germans were running out of proper alloying elements like molybdenum. They were trying to compensate with heat treatment, but the results were armor that might shatter rather than deflect incoming rounds. Some plates were properly hardened and would resist penetration, while others were brittle and would crack or spall dangerously when hit. The gun sight was a masterpiece of optical engineering, with clarity and magnification that exceeded anything the Americans had produced. But it required precise calibration that would be nearly impossible to maintain in field conditions. The radio equipment was sophisticated but delicate, prone to failure from vibration and moisture. Even the driver's controls were needlessly complex, requiring extensive training to operate effectively. Lieutenant Colonel Harrison, who'd been sent from the Ordnance Department to oversee the evaluation, called a meeting 3 weeks into the examination. The conference room at Aberdeen was packed with engineers, mechanics, and intelligence officers, all eager to hear the preliminary findings. "Gentlemen," Harrison began, "what we're looking at here is a fundamental misunderstanding of what makes an effective weapon of war. The Germans have confused mechanical sophistication with combat effectiveness. They've built a tank that would be impressive in a peacetime demonstration, but falls apart under the realities of combat." He pulled down a chart showing comparative maintenance requirements. A Sherman tank requires basic maintenance every 100 hours of operation. This maintenance can be performed by the crew with standard tools in about 2 hours. The Panther requires specialized maintenance every 50 hours, and that maintenance requires trained technicians with specialized tools. It takes 6 to 8 hours minimum. The room was silent as the implications sank in. In a war of attrition, where tanks needed to be kept running day after day, week after week, the Panther's maintenance requirements alone would cripple its effectiveness. But the real shock came when they started testing the captured Panther's performance. On the Aberdeen test track, under ideal conditions with trained American drivers and full maintenance support, the Panther performed well initially. The ride was smooth, the gun was accurate, the armor seemed formidable. But within 200 kilometers, problems began cascading. First, the left final drive began making grinding noises. Investigation revealed that the straight-cut gears were already showing excessive wear, metal shavings contaminating the gear oil. Then the fuel pump gaskets failed, requiring a complete engine compartment teardown to replace. The interleaved road wheels began binding as mud from the test track worked its way between them, requiring hours of cleaning. Master Sergeant Patterson, observing the tests, made a comment that would be quoted in the final report. "This tank is its own worst enemy. It's so complex that it defeats itself before the enemy even gets a chance." The steering system provided another revelation. The Panther used a regenerative steering system that was theoretically more efficient than the Sherman's controlled differential, but it required the driver to predict turns well in advance, selecting the appropriate gear for the turn radius. Each gear had a fixed radius of turning, ranging from 5 meters for first gear up to 80 meters for 7th gear. In combat, where quick maneuvers meant the difference between life and death, this system was a liability. The driver could engage the brakes on one side to force a sharper turn, but this high-torque method of turning could cause failures of the already vulnerable final drive. Corporal Ernest Wagner, a Sherman driver with combat experience from Normandy, took the Panther for a test drive. His assessment was blunt. "In my Sherman, I can pivot on a dime if I need to. This thing? I need to plan my turns like I'm parking a locomotive. In a fight, that hesitation gets you killed." The ammunition storage was another puzzle. The Germans had placed rounds along the sides of the hull, which provided easy access for the loader but created a fatal vulnerability. Any penetration of the side armor would likely detonate stored ammunition, causing catastrophic explosions. The Americans had learned this lesson the hard way with early Shermans and had redesigned their ammunition storage accordingly. Why hadn't the Germans? The answer, the team began to realize, lay in German design philosophy itself. The Panther had been designed by engineers who were thinking like engineers, not like soldiers. Every component was optimized for performance in ideal conditions, not for the messy reality of warfare. The track system exemplified this perfectly. The tracks were held together with pins that required precise alignment. In theory, this created a stronger, more reliable track. In practice, battlefield damage or even normal wear could cause misalignment that would throw entire tracks. American tracks used a simpler pin system that might not be as theoretically optimal but could take tremendous abuse and still function. The track life was supposed to be 2,000 to 3,000 kilometers, but in practice they often failed much sooner due to the excessive weight and stress. By week 4 of testing, the captured Panther had suffered 3 major breakdowns, each requiring extensive workshop time to repair. The same tests on a Sherman M4A3 resulted in 0 breakdowns and only routine maintenance requirements. Captain Mills compiled his thoughts in a preliminary memo that would shock officials in Washington. The Panther represents a fundamental failure to understand the requirements of modern mechanized warfare. It is a tank designed for a war that exists only in the minds of its designers. A war where tanks have unlimited maintenance support, operate in ideal conditions, and engage enemies at their leisure. In the actual war we are fighting, with its demands for reliability, maintainability, and sustained operations, the Panther is inferior to our Sherman in every practical measure. The metallurgical analysis revealed even more troubling facts. Technical Sergeant Raymond Anderson, a metallurgist from U.S. Steel who'd been commissioned for the war effort, spent days analyzing armor samples. His findings were sobering. They're trying to maintain face hardness specifications with steel that doesn't have the proper carbon content or alloying elements. It's like trying to bake bread without yeast. You can go through all the motions, but you won't get the result you need. The Panther's weight distribution added another layer of problems. At 45 tons, it was significantly heavier than the Sherman's 30 tons. But this weight wasn't distributed efficiently. The front was heavily overloaded, putting enormous stress on the forward road wheels and the final drive. The tracks, at 66 centimeters wide, still created high ground pressure that caused the tank to sink in soft ground where Shermans could pass easily. During one test, they attempted to cross a muddy field that Sherman tanks had traversed without difficulty. The Panther sank to its hull bottom within 50 meters. It took 2 recovery vehicles and 6 hours to extract it. The German emphasis on armor protection had created a tank too heavy for the infrastructure and terrain of Western Europe. The electrical system presented its own set of over-engineering failures. Where American tanks used simple, robust 24-volt systems with easily replaced components, the Panther employed a complex electrical system with specialized components that couldn't be field replaced. A single failed relay could disable entire subsystems, requiring depot-level maintenance to repair. Specialist Frederick Harper, an electrical engineer from General Electric, traced the Panther's wiring over several days. His conclusion was damning. They've created multiple single points of failure throughout the electrical system. It's like they designed it to fail at the worst possible moment. The cooling system, compromised by the deep fording modifications, struggled to keep the engine at operating temperature even in the mild Maryland autumn. The radiator fans, driven by a complex hydraulic system tied to the main engine, would fail if hydraulic pressure dropped. When the fans failed, the engine overheated within minutes, potentially causing catastrophic damage. During one test, the Panther's engine temperature soared past safe limits after just 30 minutes of operation. The test had to be halted while the engine cooled, a process that took 2 hours. In combat, such a delay would be fatal. The ergonomics of the Panther also revealed the disconnect between German designers and combat reality. The driver's position was cramped and poorly ventilated. The complex array of controls required extensive training to operate effectively. The commander's cupola, while offering good visibility, was difficult to exit quickly in an emergency. Staff Sergeant William Turner, a tank commander with experience in Italy, sat in the commander's position for an extended period. "After an hour, my back is killing me," he reported. "The visibility is good, but I can barely move. If we had to bail out under fire, half the crew would never make it." The gun, for all its impressive ballistics, had its own problems. The long barrel, extending far beyond the hull, made the tank difficult to maneuver in confined spaces like villages or forests. The gun's weight also put enormous stress on the turret traverse mechanism, contributing to premature wear. The bore required meticulous cleaning after every 20 rounds to maintain accuracy. In combat, where tanks might fire dozens of rounds in quick succession, such maintenance was impossible. As October arrived at Aberdeen, the team had accumulated enough data to draw definitive conclusions. The Panther was not the super weapon German propaganda claimed. It was not even a particularly good tank by practical standards. It was an over-engineered, over-complex machine that represented a fundamental misunderstanding of armoured warfare. Colonel Harrison called a final meeting with senior ordnance officials and intelligence officers. The room was packed with brass from Washington, all eager to hear the final verdict on Germany's most feared tank. "Gentlemen," Harrison began, "the Panther tank is a testament to what happens when engineering perfection becomes the enemy of combat effectiveness. Every aspect of this vehicle has been designed to achieve theoretical superiority at the cost of practical functionality." He presented slide after slide of data. Mean time between failures. Panther final drives, 150 kilometers. Panther engines, 1,000 to 1,500 kilometers. Sherman overall systems, over 2,000 kilometers. Maintenance hours required per 100 hours of operation. Panther, 64 hours. Sherman, 12 hours. Crew training time to basic proficiency. Panther, 200 hours. Sherman, 50 hours. "But sir," interrupted a brigadier general from the intelligence section, "how do we explain the Panther's fearsome reputation? Our troops are terrified of these things." Harrison nodded. "The Panther is indeed formidable in ideal conditions, when it's fully functional, fully maintained and engaging at optimal ranges, but those conditions rarely exist in actual combat. For every Panther that achieves a spectacular success, multiple Panthers break down before reaching the battlefield or during operations." The implications were staggering. The Germans, renowned for their engineering prowess, had engineered themselves into a corner. They had created a tank that looked magnificent on paper but failed in the field. They had prioritized complexity over reliability, precision over durability, sophistication over practicality. Lieutenant Crawford, who had spent more time inside the Panther than anyone else on the team, offered a final observation. "The Germans built a tank for engineers to admire. We built tanks for soldiers to fight in. That's the difference between winning and losing this war." The examination of the Panther also revealed something about German industrial philosophy that extended beyond just tank design. The same over-engineering mentality infected their entire war production. From the unnecessarily complex G-44 rifle to the mechanically temperamental Me-262 jet fighter, German weapons were consistently over-designed and under-tested. This wasn't just a technical failure, it was a cultural one. German engineers, raised in a tradition that valued precision and complexity, couldn't adapt to the requirements of total war. They couldn't accept that good enough today was better than perfect tomorrow. They couldn't understand that in war, quantity has a quality all its own. The American approach, exemplified by the Sherman, prioritized different values: reliability over performance, ease of production over mechanical sophistication, maintainability over optimization. These weren't compromises, they were conscious choices based on a clear understanding of what modern war required. The Sherman could be produced by automobile workers with minimal training. Its parts were interchangeable between variants. It could be maintained by farm boys who'd grown up fixing tractors. It could run on multiple fuel types. It could be recovered and repaired quickly. It could be shipped easily. It could be upgraded continuously. These weren't accidents. They were the result of deliberate design decisions. As the team wrapped up their investigation, they discovered one final irony. The Panther's gun sight, that masterpiece of optical engineering, was calibrated for engaging targets at 2,000 meters or more. But analysis of combat reports showed that the average tank engagement range in Europe was less than 800 meters. The Germans had optimized for a kind of combat that rarely occurred. The maintenance manuals captured from the Panther revealed the full extent of the over-engineering disaster. Simple tasks required specialized tools that were often unavailable at the front. The manual for replacing a final drive was 47 pages long and required 18 specialized tools. The equivalent procedure for a Sherman was 3 pages and could be done with standard tools. To reach the final drive for repair, the entire driver's compartment and transmission had to be disassembled and lifted out, a process that could take an entire day under ideal conditions. Sergeant Patterson, reviewing the maintenance requirements, made a calculation that stunned everyone. To keep a company of 17 Panthers operational requires the same maintenance infrastructure as a battalion of 50 Shermans. That's not a tank, that's a liability. The captured Panthers' test runs continued to reveal new problems. The torsion bar suspension, while providing an excellent ride, was prone to failure and nearly impossible to repair in the field. When one bar broke during testing, it took the Aberdeen maintenance team, with full workshop facilities, 2 days to replace it. In combat conditions, the tank would have been abandoned. The interleaved road wheel system created another unexpected problem. In cold weather, mud that worked its way between the wheels would freeze overnight, effectively immobilizing the tank until it could be thawed and cleaned. Soviet forces had reported finding abandoned Panthers frozen in place, their crews having fled rather than spend hours chipping ice from the suspension. Even in moderate weather, the buildup of mud between the wheels could add tons of extra weight to the vehicle, further straining the already overtaxed drive system. The Panther's size also worked against it. At over 8 meters long and nearly 3 meters tall, it presented a large target. It couldn't use many bridges that Shermans crossed easily. It couldn't navigate narrow European streets without difficulty. It couldn't be easily concealed. It couldn't even fit in standard railway cars without special modifications. During transportation tests, the team discovered that moving a Panther by rail required removing the outer road wheels and installing narrower transport tracks, a process that took a trained crew 4 hours. Shermans could be loaded and transported without any modifications. This meant that strategic mobility, the ability to quickly move tanks to where they were needed most, was severely compromised for the Panther. The cumulative effect of all these design failures was a tank that looked impressive in propaganda photos, but failed to deliver on the battlefield. The Panther represented the triumph of theoretical engineering over practical experience, of perfectionism over pragmatism. As November arrived and the investigation wound down, the team prepared their final report. It would run to over 300 pages, with detailed appendices covering every aspect of the Panther's design and performance. But the executive summary was just 1 paragraph. The German Panther tank represents a fundamental failure to understand the requirements of modern mechanized warfare. Its overcomplex design, excessive maintenance requirements, and poor reliability make it inferior to the M4 Sherman in all practical combat applications. While individual components may demonstrate superior engineering in isolation, the complete system fails to provide the combination of reliability, maintainability, and effectiveness required for sustained combat operations. The Panther is not a superweapon. It is a cautionary tale of how over-engineering can defeat its own purpose. The report was classified and distributed to key commanders and industrial leaders. Its implications went far beyond just tank design. It revealed a critical weakness in German war production that the Allies could exploit. If the Germans were wasting resources on over-engineered weapons that failed in the field, then the Allied strategy of mass production of reliable, adequate weapons was even more valid than previously thought. Back in Germany, Panther crews continued to fight and die in their over-engineered machines, unaware that their supposed technological superiority was actually a millstone around their necks. Tank commanders who should have been leading attacks were instead managing mechanical failures. Maintenance crews who should have been keeping tanks operational were instead performing complex repairs that shouldn't have been necessary. One German report from early 1944 noted that a Panther battalion required 118 separate repairs in just 5 days of operations. Of 30 Panthers that started an attack, only 4 remained operational by the end of the day, not from enemy action, but from mechanical breakdowns. The most common failures were final drives, followed by transmissions, then engines, then fuel pumps. The German tank designers, isolated in their factories and design bureaus, continued to add complexity to new designs. The Panther II, Tiger II, and even more ambitious projects like the Maus Super Heavy tank all exhibited the same fundamental flaws: over-engineering, excessive complexity, and impossible maintenance requirements. They seemed incapable of learning from the Panther's failures, trapped in a design philosophy that valued theoretical perfection over practical functionality. Meanwhile, American factories continued to turn out Shermans by the thousands. Each one might not have been as theoretically impressive as a Panther, but each one would actually make it to the battlefield, fight effectively, and keep fighting day after day. In modern war, That reliability was worth more than all the precision engineering in the world. The captured Panther at Aberdeen would continue to be studied throughout the war, teaching American engineers valuable lessons about what not to do. It served as a reminder that in warfare, perfection is the enemy of good enough, and that the best weapon is the one that actually works when you need it. Years later, Captain Mills would reflect on the investigation in his memoirs. The Panther taught us that the Germans had forgotten a fundamental truth of warfare, that battles are won not by perfect machines, but by adequate machines that actually work. They built a tank to impress engineers. We built tanks to win wars. The investigation's findings would influence American tank design for decades. The emphasis on reliability, maintainability, and practical effectiveness over theoretical superiority would become hallmarks of American military equipment. The M26 Pershing, M47 Patton, and subsequent American tanks would all reflect lessons learned from examining the Panther's failures. German veterans, interviewed after the war, would confirm what the Aberdeen team had discovered. One former Panther commander stated simply, "We spent more time fixing our tanks than fighting in them. The Panther was our burden, not our strength." Another veteran, a maintenance officer with the 2nd SS Panzer Division, was even more blunt. The Panther was designed by people who never had to maintain a tank under fire, never had to change a road wheel in a freezing Russian winter, never had to explain to a crew why their tank was deadline again. It was a designer's dream and a mechanic's nightmare. The economic impact of the Panther's over-engineering was equally devastating. Each Panther cost approximately 117,000 Reichsmarks to produce, compared to 46,000 for a Panzer IV. But the Panther didn't deliver proportionally greater combat effectiveness. The resources spent on one Panther could have produced 2.5 Panzer IVs, which would have provided far greater combat power. The man-hours required to build a Panther were equally excessive. German factories needed 55,000 man-hours to complete one Panther. American factories were producing Shermans in 10,000 man-hours. This 5-to-1 disadvantage in production efficiency meant that even if the Panther had been a superior tank, Germany could never have produced enough to matter. By the end of the war, America had produced over 49,000 Shermans. Germany managed to build fewer than 6,000 Panthers. The Panther's development history revealed another aspect of the over-engineering problem. The original specifications called for a 30-ton tank with reasonable armor and mobility. But Hitler's personal intervention repeatedly demanded more armor, a bigger gun, more features. Each change added weight and complexity without proportional benefit. The final production Panther bore little resemblance to the original concept. It had grown from 30 tons to 45 tons. Its armor had increased from 60 mm to 100 mm on the glacis. Its gun had grown from the planned shorter version to the long L divided by 70. Each increase made the tank theoretically more formidable but practically less effective. This pattern of specification creep, driven by Hitler's obsession with superior numbers on paper, infected the entire German armaments industry. Weapons that should have been simple and reliable became complex and fragile. Production that should have been straightforward became complicated and slow. The Panther's fate in combat revealed the ultimate cost of over-engineering. At the Battle of Arracourt in September 1944, newly formed German Panzer brigades, equipped primarily with factory-new Panthers, engaged American forces. Despite having newer tanks with theoretically superior armor and firepower, the Germans suffered devastating losses. They lost approximately 200 tanks over 11 days of fighting, while American losses were fewer than 50 vehicles. Many of the German losses came not from direct combat but from mechanical failures, lack of fuel, and abandonment by crews when their complex machines broke down. The fog that should have given the Germans an advantage instead negated their superior optics and gun range. American Sherman crews, trained in aggressive maneuver tactics, used the poor visibility to close distance and engage Panthers from the flanks. The Panther's poor reverse speed and complex steering system made it difficult for German crews to respond to these tactics. Time and again, Panthers were caught unable to maneuver effectively. their theoretical advantages meaningless in the close-quarters battle that developed. One American tank destroyer commander reported, "We'd see Panthers coming at us and think we were done for. Then they would stop moving, not from our fire but from mechanical failure. We'd pick off the immobilized ones while the rest tried to withdraw. Their best tank was its own worst enemy." The psychological impact on German crews was devastating. Tank crews who had been told they were operating superior machines lost faith when those machines repeatedly failed. The constant mechanical problems, the endless maintenance requirements, the frequent breakdowns, all eroded morale and combat effectiveness. Many Panther crews developed a fatalistic attitude, knowing that even if they survived enemy fire, their tank probably wouldn't survive the mechanical stresses of combat. One captured German tank driver told interrogators, "We were more afraid of our own tank breaking down than of enemy fire. At least against the enemy, we could fight back. Against a broken final drive, we were helpless." The Panthers' legacy would be one of missed opportunity. Germany had the technical capability to produce excellent tanks. The basic concept of the Panther, a medium tank with good armor and firepower, was sound. But the execution, driven by over-engineering and unrealistic specifications, turned potential success into actual failure. Had the Germans stayed with the original 30-ton design, accepted reasonable rather than perfect performance, and prioritized reliability over sophistication, they might have produced a war-winning weapon. Instead, they created a maintenance-intensive liability that absorbed resources without delivering proportional results. The Aberdeen investigation revealed one final, crucial truth. The best weapon system is not the one with the best specifications on paper, but the one that best fits the totality of warfare: production, logistics, training, maintenance, and combat. The Panther failed not because it was a bad tank in theory, but because it ignored the practical realities of war. As World War II entered its final months, American tanks continued to press forward, while German tanks increasingly sat immobilized by mechanical failures. The writing was on the wall, not in the grand battles of tank versus tank combat that German designers had imagined, but in the mundane reality of broken final drives, failed fuel pumps, and over-complex systems that couldn't survive the harsh realities of war. The engineers at Aberdeen Proving Ground had discovered something profound in their examination of the Panther. They had learned that in war, as in life, perfection is often the enemy of good enough. The Germans had tried to engineer the perfect tank and instead had engineered their own defeat. The investigation's final conclusion was both simple and profound. The Panther was not a superweapon that failed to live up to its potential. It was a fundamentally flawed concept that represented a complete misunderstanding of what modern warfare required. Its over-engineering wasn't a minor flaw to be corrected, but a fatal error that doomed it from the start. The last entry in Captain Mills's investigation notes captured the essence of what they had discovered. The Germans built a tank to win an engineering competition. We built tanks to win a war. The Panther proves that in warfare, the difference between these two goals is the difference between victory and defeat. As the captured Panther was wheeled into long-term storage at Aberdeen, it carried with it the lessons of its failure. Future generations of American tank designers would study it, not to copy its sophisticated systems but to avoid its fundamental mistakes. It would serve as a permanent reminder that in the brutal arithmetic of war, reliability beats sophistication, quantity has a quality of its own, and the best engineering is often the simplest. The German engineers who had designed the Panther with such pride, who had crafted each component to standards of precision that exceeded anything the Allies were producing, had failed to understand the most basic principle of military engineering. The perfect weapon that doesn't work is infinitely inferior to the adequate weapon that does. The Panther would go down in history not as the fearsome predator its name suggested, but as a cautionary tale of engineering hubris. It was a tank defeated not by enemy fire, but by its own complexity, a war machine brought down not by opposing armor, but by its own impossible standards. In the end, the American engineers at Aberdeen Proving Ground had discovered the truth that would have devastated German tank crews had they known it. Their vaunted Panther, their technological masterpiece, their supposed proof of German engineering superiority, was actually proof of something very different. It was proof that in the harsh reality of mechanized warfare, over-engineering wasn't an advantage, it was a fatal flaw that helped lose a war.